Hey y'all, it's me, Miss B, and today we're talking about the dot product of two vectors. So the dot product of two vectors returns a scalar, which if you remember from your last notes, it's just a regular number, a constant to be more specific. All right, so if we have the dot product of u and v, where you have our components written there, it's going to be u dot v is equal to our first component of u times our second component of v plus our second component of u times our second component of v. All right, it's a pretty easy formula, so let's go ahead and make sure we are able to do this. Make sure your this is multiplication, and then your dot is a little bit bigger, so make sure you're differentiating between those two things because they don't really mean the same thing. Okay, so I'm gonna go ahead and take these and write out their component form of them. So this is 1, 6, 3i minus 2j would be 3, negative 2, and negative 4j would give me 0, negative 4. So I do that just so that, especially with problems like that we have just one term, we know how to easily reference those. Okay, so u times v is going to be 1, 6 dot 3, negative 2. So if this is our u1, u2, v1, v2, then we can write this out as 1 times 3 plus 6 times negative 2. So we get 3 plus negative 12 or negative 9 for that answer. All right, let's go ahead and jump into this next example. So I have u dot v times w. So I have this right here will produce a scalar, and this right here is a vector. So I should get a vector as my answer if we do everything correctly. So let's go ahead and write out 1, 6 dot 2, negative 3, negative 2. And that's all times w, which is 0, negative 4. So I'm going to kind of highlight my parentheses here to make them a little bit more defined. Do this math. We have 1 times 3 plus 6 times negative 2. Then we have 3 minus 12 times that scalar, or times that function. So we have negative 9 times that vector. Distributing that 9 through, we get 0, 36 for that final vector. So that is how we do those multi-step problems. We want to do them in order. Okay. So then we want to do u times 3w. So we are going to do 1, 6 dot 3, 0, negative 4. Okay. So for this one, we want to distribute that 3 through first. So we have 1, 6 dot 1, 6 dot 3, 0, negative 12. So then that's 1 times 0 plus 6 times negative 12. 0 plus negative 72 equals negative 72. Finally, this last one here, we've got u dot u. So 1, 6 dot 1, 6. All right, let's go ahead and do 1 times 1 plus 6 times 6. If you'll notice, this is 1 squared plus 6 squared, which is 1 plus 36. equals 37. All right, the reason why I wrote this step out is because it's going to lead into something else. Okay, so we're going to cover the dot product of something times itself in the next section. Okay, so we can find the magnitude using the dot product. So if we take the dot product of vector in itself and take the square root, we can find the magnitude. So here we have u dot u equals the magnitude of u squared, or we've got the square root of u dot u equals the magnitude of u, and we'll really just use this one right here. Okay, so fix this really fast. Okay, so let's find the magnitude of v, which is 3i minus 7j, using the dot product. So we can rewrite this as, oh goodness, 3 negative 7. So we want to take let's say the magnitude of v is equal to the square root of v dot v. So square root of 3 negative 7 dot 3 negative 7. So if you look back to this last problem, we end up with our first term squared times our second term squared right here. So I'm going to go ahead and write that out just to save us a little bit of time. So we end up with getting the square root of 3 squared plus negative 7 squared. So that is 9 plus 49, which is the square root of 58. Now, 7 squared, so the square root of 49 is 7, and the square root of 64 is 8. And we know that 58 is somewhere in between there. It's about 7.6. So that right there is our magnitude of v. Okay, so this leads into work done. All right, the work done by a force acting along the line of motion is the magnitude of the force times the distance, which can be written as F dot D. If the force is angled, the component force that is in the same direction as the movement counts. So this is going to play into some of the problems that we're going to do. All right, so we can take the work by taking the dot product of movement and force vectors. Before we begin, here are units. The English measurement system uses the foot-pound, and the metric system uses the Newton meter, also known as a joule. All right, so here is our first example. So we have a 75-pound stone is lifted 10 feet into the air. Determine the amount of work done. So I'm going to draw a picture. It's not going to be real pretty, but here I have a stone being lifted into the air, and it's 75 pounds. And it's going 10 feet into the air. Okay, so this right here, let's actually relabel this. This is 75 pounds, and then this is 10 feet in the air. So this is 0, 0, and all of a sudden it's going to, if we were to look at this as like an axis here, it's going to 0, 10. So because of that, this vector right here is written as 0, 10, just like that. Let me actually make my pen a little smaller so we don't run out of room. we've got 0, 10 for that movement. Okay, and then we're gonna have our second one as 75 pounds. Now that's gonna be written as 0.75 for that vector. So then we'll go ahead and find and this is our force, so we want to find the dot product of F. Let me change color here. Work is equal to the dot product of F and D. So we'll do force is 0.75, distance is 0.10. So that's 0 times 0 plus 75 times 10. So that is going to be 750, and we want to label it as feet per pound. Okay, so we just really want to, the hardest part is going to be drawing the picture on these. All right, let's do this next one. So a 75 Newton force directed 28 degrees above the horizontal pulls an object 8 meters. Okay, so this is where that comes into play, where it says that if the force is angled, only the component of the force that is in the same direction as the movement counts. So that's gonna play into drawing our picture. Okay, so here I'm gonna just draw, here's my thing. This is the force. So think of it kind of as like a wheelbarrow. Got like a little thing here. It doesn't say what it is, but it's being pulled this way by its handle. But it's traveling this way. All right, so that's what that means. It's being pulled above the horizontal, and that's 28 degrees, but it's being pulled 8 meters. So if we were to say this is 0, 0 right here, then it's going to 0, 8, or I'm sorry, 8, 0. Then that movement vector, or RD, is going to be 8, 0. Okay, then our force vector, this is a little bit harder and a throwback to last chapter, but we've got F is going to be equal to our magnitude of V cosine theta, magnitude of V sine theta. So this force vector with the 28 degrees is going to be, our magnitude is 75, cosine of 28 degrees, and then we have 75 sine of 28 degrees. Okay, and then we'll put the two together. So we're doing force label correctly times dot with direction. All right, so then we end up getting 8 times 75 cosine of 28 degrees plus 0 equals so that's, nope, 8 times 75 cosine of 28. I want to make sure our calculator is in degrees, and it is. So we have 529.76. So we'll leave it as 529.8, and that is joules because it's Newton meters. All right. So for this next one, go ahead and draw a picture.